So, we talked about two phenomena coming from Lorentz transformation. One was length contraction and other time dilation. So, length contraction is when you have a length to be measured, length of a material object or just distance between 2 points, any length that you are measuring. If you measure it from a frame in which that length is not moving, that is the largest length called rest length or proper length. And if you see from any other frame in which this length is moving in its own direction, then in that direction the length is less. So, that is known as length contraction. Of course, the lengths perpendicular to the direction of motion, they do not contract, y prime is y, z prime is z. So, is the length parallel to the velocity, that is smaller than the rest lengths. So, that is length contraction. We say that proper length or rest length same as rest length that is equal to, this should be largest and therefore, it should be improper length or moving length and then divided by square root of 1 minus v square by c square. So, that is about length contraction. And then time dilation, if we have two events and there is a time interval between these two events. So, if there is a frame in which these two events have taken place at the same position, then from that frame if you measure the time difference, the time interval, it is called proper time interval. And if you see from some other frame in which one event takes place at x equal to x 1, other takes place at x equal to x 2 somewhere else, then the time interval measured from that frame will be more. So, that is known as time dilation. So, in time dilation what we say, proper time interval, and remember proper time interval means time interval between two events which have occurred at same position. So, if you are able to find such a frame, then the time interval between those two events measured in that frame is called proper time interval, and this is the smallest among others. So, this is improper time interval and then multiplied by square root 1 minus v square by c square. So, these are two very famous and important results which come from the Lorentz transformation and which are verified or which they do occur in nature in this particular fashion. In experimental labs, it is not very difficult nowadays to have particles with a speed close to c. Particle accelerators are there. So, in those accelerators, the speed of the particle is taken to very, very high values, and therefore, all these results can be verified, can be checked. The mathematics done with these results, they only reflect the results of those experiments and other things. So, must believe it. Now, this proper time interval and improper time interval, they are connected by this. This can also be termed in a different fashion how the clocks run. So, suppose you have a clock and that clock is suppose you have a clock and this clock tells the time t equal to t 1, this is event E 1, and after some time this same clock that gives me time t equal to t2. So, these are two different events, clock reading time t1, that is the first event, and then clock reading time t2, that is the second event, and the time interval between this time interval delta t is t2 minus t1. That is the time interval, and this is proper time interval. I am looking from a frame in which this clock is fixed, and therefore, the two events have taken place at the same position, and hence this time interval is the proper time interval. What happens if I see it from some other frame? Suppose this frame, let us write this frame as S frame. So, in this frame, this is fixed, x is equal to some x naught, this position is fixed, and then first event is this and second event is this, and this is the time interval. Now, suppose I look at these events from some other frame, S prime frame, event. So, that this will take place at t1 prime, that will be t1 and minus x naught v by c square divided by square root 1 minus v square by c square. Okay. Then event 2, which has occurred at the same position x equal to x naught, but t equal to t2 in this frame. If this event E2 is looked from this S prime, and the question is asked when did this occur, the time will be t2 prime is equal to t2 minus x naught v by c square and then roots 1 minus v square by c square, and therefore, t2 prime minus t1 prime is equal to t2 minus t1 and divided by square root 1 minus v square by c square. Same equation that we got for improper time interval and proper time interval, because this is proper time interval and this is improper time interval. In this frame, the first event has taken place somewhere, and the second event which has taken place at a later time. So, this clock must have moved to some other place and therefore, improper. So, that same relation is here, but now you can interpret it as how the clock is running as seen from S prime frame. How much time elapsed? This much time elapsed, and the clock advanced from t equal to t1 to t equal to t2, because the reading is t equal to t1 and here the reading is t equal to t2. So, this clock has advanced on its dial t2 minus t1, whereas the time elapsed, I am talking from here, time elapsed is this much and that is this much, and this is greater than t2 minus t1. So, time t2 minus t1 by square root 1 minus v square by c square is elapsed, but the clock has advanced only by t2 minus t1. Okay. t2 minus t1 is smaller and t2 minus t1 divided by square root 1 minus v square by c square is larger. So, a larger time has elapsed, but on the clock it is showing a smaller advancement. So, the clock is running slow. According to S prime, the clock of S is running slow. A time this much has been elapsed, but the clock has advanced by a smaller amount t2 minus t1. So, this is running slow. So, this time dilation thing can also be phrased as moving clocks run slow. This run is how the clock is showing time, at what rate the clock is showing time, and the clock is moving, that running is different. So, moving clocks run slow, that is a good phrase to remember, and it tells that if you have a frame in which the clock is fixed, in that frame clock runs at the right rate, at the correct rate, but the same clock when seen from some other frame in which it is moving, it is running slow. So, that is moving clocks run slow. Now, today I will take another phenomena which comes from Lorentz transformation, and of course, which does take place in our nature, and that is known as relativity of simultaneity. So, relativity of simultaneity. What does it mean? Two events are simultaneous, that means they occur at the same time, at the same instant. This simultaneity is also relative. In one frame the two events may be simultaneous, but in other frame they may not be simultaneous. One has occurred before the other, that is possible. So, simultaneity is not a universal thing, two events have taken place at the same time. It is not a universal fact, it depends on the frame, from which frame you are looking at, and therefore, different frames will look at these two events. The ordering of those two events may be different in different frames. So, that is known as relativity of simultaneity. First, let me take an example. Suppose you have a long tube box, and here there is a door D1 and here there is a door D2, and right at the middle there is some source of light, and then this emits light in all directions, one going in this direction, one going in this direction. At the same time the pulses are emitted, and the mechanism is such that when this light hits this door D1, when this light hits door D1, this is in fact one event, I can just rename it, and then the door D1 opens. So, our electronics is such that this light falls here, and then this door D1 that opens. So, this is one event. Next event is this pulse which falls on that D2. So, light hits D2, this is another event, and you can rename it door D2 opens. Now, if this light source is right at the middle of this D1 D2, then obviously the two events have taken place simultaneously. Door D1 and D2 have opened simultaneously. Now, if you look at this whole experiment once again from a frame, let us say this frame is S, and I look at from a frame S1, and with respect to this S, this S1 is going towards right with some velocity. So, from here I am looking at. So, from S1 what I will see? I will see that this whole tube is going towards left. So, at a certain instant the source was put on and it emitted 2 light beams. Light beams are going, or light pulses are going in frame S1 also at a speed c, because the speed of light in vacuum is same in all inertial frames. So, this light is going with speed c, this light is going with a speed c, this door D1 is going towards left with velocity v, D2 going left with velocity v. That is the scenario from here. So, from this frame, if you analyze things, it is that this light is emitted, and this is going at c, this is going at c, but then this door D1 is going towards left with velocity v, and this door D2 is going towards left with velocity v. So, you can see that door D1 is going towards left and this light has to catch up with that, and therefore, this meeting of this light pulse and this door D1 is not going to be here, it is going to be somewhere here, extra distance. And so, this light has to travel this much distance to reach this door D1. On the other hand, when light pulse is emitted, D2 is here, and therefore, the D2 is coming in this direction. So, meeting of this pulse and D2 will be somewhere to the left of this D2, and hence this pulse will travel a smaller distance, but then the speed is same, the speed of this pulse and this pulse is same. So, it has taken longer time and this has taken shorter time, and therefore, this D2 opens before D1. So, the two events which are simultaneous in S are not simultaneous in S1. D2 opens before D1. You can think of yet another frame S2, which is going in this direction, and from this S2, if you look at this whole experiment, from this S2, if you look at this experiment, this whole tube is going towards right, and hence it is something like this. You have D1 here, D2 here, this is going towards right, this is going towards right. From the middle, the light pulses are emitted, and since it is going towards the light pulse, the meeting point will be somewhere here, shorter distance, and this is going in the same direction as this light pulse, meeting will be somewhere here. So, longer distance. So, this door D1 will open before D2. So, you can see in one frame D2 opens before D1, in some other frame D1 opens before D2, and in some other frame the two are opening together. So, two things are simultaneous, this is also relative. You can see this from Lorentz transformation also. If you have two events occurring at say x1 and x2 and time t, let us say time t is simultaneous here. At the same time an event occurs here, at the same time an event occurs here. This is, let us say, S frame. Now, if these two events are seen from S prime frame, what will be the time? So, if this is event E1 and if this is event E2, then for E1 you can write, T1 prime is equal to T minus x1 v by c square by square root 1 minus v square by c square, and for E2 you can write T2 prime is equal to T2 and minus x2, here it is x2 v by c square, and then divided by square root 1 minus v square by c square. And if you subtract T2 minus T2 prime minus T1 prime, you subtract, this is at same t. So, here it is t, this T2 and this T1 are same as t here and t here. So, this is T1 and this is T2, both are t. So, both here also you have to write t and here also you have to write t, and you subtract and this cancels out. This cancels out, and then if you take this minus v by c square common, x2 minus x1, and then divided by square root 1 minus v square by c square. So, what you see, T2 prime minus T1 prime is not 0. So, they are not simultaneous. X2 minus x1 in this diagram is positive, and you have a minus sign here. So, you find that T2 prime is, this is positive. So, the whole thing is negative. So, this is smaller than T1 prime. So, the things which are simultaneous in one frame are not simultaneous in the other frame. And if you take another frame which is not S prime, this we are writing from S prime frame, and remember S prime goes in the direction positive x axis. So, if you have a third frame which is going in the opposite direction, only thing you have to do, write v equal to minus v. So, if you do v equal to minus v, then this whole thing will become positive, and then T2 prime will be greater than T1 prime. So, in some frame it is simultaneous, in some frame this event occurs before that event, and the other frame it is opposite. So, ordering of events may not be same in all frames, that is the relativity of simultaneity. But then if x2 minus x1 is 0, suppose x2 minus x1 is 0, x2 and x1 are same position. In that case, if two events are occurring there itself and they are simultaneous, they will remain simultaneous. So, this is about relativity of simultaneity. The next topic will be very interesting, and that is synchronization of clocks. If you have two clocks, normally if they are, everything is all right, they should be synchronized. That means, at the same time I look at this, at the same time I look at this, the two readings on the clock should be same. We say that it is synchronized. Now, in one frame I have so many clocks, and by meticulous mechanisms we synchronize everything. All clocks are showing the same time at any given instant, they are synchronized. What happens if I look at these clocks from a different frame? All these clocks are then moving in one direction, and from that other frame I am asking this question, at this instant what is the reading of this clock, what is the reading of that clock? And what we will find is they are not same. So, clocks which are synchronized in one frame, they are not synchronized in the other frame. So, that is the topic that we will take up in next lecture.